Today we're going to look at section 8.2 from chapter 8 in the core pure book year 2, simple harmonic motions. So this is second order differential equations that are going to be used in real life situations, well, up their applications to almost real life situations to begin with. It's all about simple harmonic motion. So what is a harmonic motion? So we're talking about an object, a particle that is following a motion of vibration. So anything that's repetitive and vibrating, it will, if there are no forces stopping the movement and it can vibrate for a long time, it will follow simple harmonic motion. So in short, we're going to use SHM, simple harmonic motion. So you could have a particle that follows a repetitive motion. So you could say vibration, oscillation, moving up and down. So that kind of harmonic motion, it's also called. So what are we saying there? If a particle follows a simple harmonic motion, then the acceleration, which is x dot dot, so displacement differentiated twice, is directly proportional to the displacement. But it's the constant of proportionality is a negative number. So K, in fact, for those of you who do physics, is equal to omega squared, where omega is what we called angular velocity. So it's something, if you are studying further mechanics, you will study circular motion, so you know all about angular velocity. Let me just get to that point there and write angular. What was it writing over there? Hold on. Whatever reason doesn't want to write that. So angular velocity. That's better. Okay, so as long as a particle follows this motion, so this is the equation describing it, then we know that we are talking about simple harmonic motion. Now let me talk to you about what the graph of the displacement against time might look like. Okay, so if a particle, and it's just common sense, there you go. If it follows a simple harmonic motion, then it will follow like a transformed sine graph. So the simplest one, it could be like this. Okay. It could be the graph, a cos graph, which is sine graph transformed. It could be a sine graph shifted. Okay, so in general, the solution to the differential equation, which will be representing the displacement, will look like so. So let's say r sine maybe, and it's going to be, let's say omega t, some constant t, and it's actually going to be always omega t, or just don't have to worry, a number of t's, plus or minus alpha maybe, because it's shifted, could be shifted. So let me just show you, I mean, this is just a graph of sine graph that doesn't have plus alpha in here. So this value here is going to be the maximum displacement, okay? and it's equal to r if you look at my graph. It's also called amplitude. Okay, so it's another example of simple harmonic motion could be tide or changes, daily changes in temperature, so they go up and down. Okay, now the one oscillation to happen, okay, is from here to here. The time it takes, let's say t, it's called period. And the period of that normally is 2 pi, but because we have multiplied our little t by omega, it's going to be omega times as fast. So if omega was 2, it would be twice as fast. So we'll shorten the period of 2 pi by 2 then, but here by omega. So that's the period of our movement. There you go. So another key interesting fact is, if I just show you maybe the examples of simple harmonic motion, could be a pendulum that swings from left to right. Okay, so if you let it go from when it's furthest to the left, it will swing up and down, and there's no forces stopping it, no air resistance, then it will keep on going. Okay, and it will follow simple harmonic motion movement. Now, if it were not let go from this position, it would hang freely with the gravity pulling on it downwards, and that would be its equilibrium position. Okay, so this is equilibrium. Equilibrium position. Okay, now if you talking about, I know, another example of simple harmonic could be a spring that is maybe attached to 2 points. There you go. And and if you imagine you're going to pull it from here to there and then let go, then it will go vibrated. Or it could be better maybe imagining it doing it this like this, hanging down. Okay, and then if you pull it down and let go, it will keep going up and down. But if you didn't pull it down and it's just hang there freely, then at that point it will be in its equilibrium position. Okay, so let's just imagine a particle then moving actually horizontally. So maybe it will be part of that spring. Okay, so O would be the equilibrium position, and let's say P is going to be the maximum displacement. There you go. And over here, that is, and that's going to be maximum displacement. So to describe the journey of the particle, imagine it's going to be positive direction if it goes towards P. Then the acceleration is always going to be negative, and it's going to be always directed towards O. So that acceleration, we're going to call it, well, I called it K before, but it could be omega squared x. Okay, so that describes the motion of our particle. Because it's negative, it's directed to the other, towards O. Now, what you could also derive is a really interesting fact. So remember, this is displacement. If you differentiate displacement, you're going to get velocity. So that is your dx dt, if you like. Okay, now if I differentiate velocity, I'll get dv dt. Okay, and that is going to be written x with 2 dots. This is acceleration. Okay, now dv dt, which is our acceleration, can be therefore written in the following way. We can write dv/dt as split it into the chain, using the chain rule, into the product of two differential. So the first one is dv/dx, so the velocity with respect to x, and then dx/dt. And if you could see, dx/dt is our velocity to begin with. So that is going to be velocity and then dv/dx. So this is quite an important result in our simple harmonic motion. I don't think you necessarily will need to know how to derive it, but it's there in the book. And the first example that we're going to go over in this video, and then the subsequent examples, because I think they are more important, will be done in the separate video, will follow now. So the first example, okay, I think it's example 3, no, example 4. Okay, so over here we've got a particle P that moves with simple harmonic motion. So as soon as they write simple harmonic motion, I'm going to write down what it means. It means that x dot is equal to, you can put minus k, but I'll put minus omega x this time. I also will write down the result from before. So what we've done is we found that the acceleration, which is x, it was can be written as v and then dv/dx. Okay. So this is the result we've just used chain rule to derive. Okay, so if you now, so that was acceleration. Okay, so if you now substitute that acceleration v dv/dx for that acceleration, what you are faced with is the differential equation that needs to be solved, because we are asked to solve it, because in part A we are going to be starting from this position, so with having dv/dx, arriving with no dv/dx. So we are going to use separating variables. So we've got the exit, make it legal, and then integrate it. So it's going to be a half v squared is equal to minus a half, remember omega is just a number, x squared plus c. Okay, but we are told that maximum displacement of the particle from O is A, so that's the maximum displacement happens. Now, if you go back to the previous page, if you are having the pendulum vibrating, so the maximum displacement here is that position over here to the right or to the left. So this is the furthest away from the equilibrium. Now, at that moment, as it turns or changes the direction of its motion, the velocity is going to be 0. So that means that at this particular time, given that the maximum displacement of the part is A, so we've got V, when V is 0, x is going to be equal to A. And that information can be substituted into the above equation to obtain the value for C. So C is going to be equal to a half omega squared A squared. So let's just sub it into this, and you're going to get a half V squared minus a half equals to minus a half omega squared x squared plus a half omega squared A squared. Okay, so we can multiply everything by a half, and we'll get V squared is equal, we can take this omega out, and then you will have minus x squared plus a squared, so a squared minus x squared. So you've proven the required result. Okay, now in part B, we will just have a quick glance at what the part B says. Show that x is equal to a sine w omega t plus alpha, where alpha is an arbitrary constant. Okay, so what I'm going to do is look at the first equation, which is over here. Okay, let me just put it in color. So this is the equation we'll be working with. Okay, and we're going to solve this differential equation using the techniques that we've used before. So this is something that you'll be solving all the time when using simple harmonic motion. So you've got x dot dot is equal to minus omega squared x, or you could say minus kx. So let's put everything on one side. Okay, so what's the auxiliary equation here? It's going to be m squared plus omega squared is equal to 0. So m is equal to plus or minus omega I. Okay, so that gives me the first, the complementary function, which is the solution. So that is going to be complex numbers, no real parts, so you won't have e part. So you have a cos omega t plus b sine omega t. Now you can actually spend time using r sine or r cos method to put it together. But we can't really, because we don't know the values of a, b, or omega. So, but we do know whenever we do have a combination of sine and cos, that can be written in the form required. So it can be converted into r sine. We can actually state what r is, and then over here we are going to have omega t plus alpha. We could say r is going to be a squared plus b squared square rooted, and you can find the expression for alpha. Better to do it when you've got some values. Okay, so I'm going to stop here, and because this video is just introduction to simple harmonic motion, we're going to be able to go on to example 5.